Hello everyone, welcome back to our educational video. Today we are going to discuss on the topic basics of radiation physics. Here we will cover introductory part as well as atomic and nuclear structure. So let us begin with introduction. The first topic that we are going to study is physical quantities and their units. So the physical quantities are characterized by their numerical value, that is magnitude, and they are associated with the units. So symbol for physical quantities are set in italic type, but the symbols for unit are set in Roman type. So and the next is numerical value. The unit of physical quantity must be separated by space. So numerical value and unit must be separated by space. For example, 21 space kg, not 21 kg. 15 space mega electron volt, not 15 mega electron volt. Currently used metric system of unit is known as System International D units, that is also called as International System of Unit or SI system. The SI unit system of a unit is founded on the base unit for 7 physical quantities. If you look into the physical quantities, the SI units are given here. Length is measured in meter, mass is measured in kilogram, time in second, electric current in ampere, temperature in Kelvin, amount of substance in moles, and luminous intensity in candela. Now, radiation are classified into two main categories. First is non-ionizing, and second is ionizing. And again, ionizing are classified into two types, that is directly ionizing, means charged particles, and indirectly ionizing, means neutral particles. So directly ionizing, that is charged particles, are electrons, protons, alpha particles, etc. And the neutral particles are photons, that is X-rays, gamma rays, or neutrons. Now, ionization photon radiation is also classified into four categories, that is characteristic X-ray, which are result from electronic transition between atomic shells, then bremsstrahlung, that is results mainly from electron nucleus coulomb interaction, then gamma rays, that is result from nuclear transition, then annihilation quantum, and these radiations are result from positron electron annihilation. Constituent particles forming an atom are proton, neutron, and electrons. Protons and neutrons are also known as nucleons and they form nucleus. The atomic number, which is denoted by Z, is the number of protons and number of electrons in an atom. Atomic mass number A, which is the number of nucleons, that is Z plus N in an atom, where Z is the number of protons or atomic number of an atom and N is the number of neutrons in the atom. There is no basic relation between atomic mass number A and atomic number Z of a nucleus, but empirical relationship, that is Z is equal to A upon 1.98 into 0.0155 A raised to 2 upon 3, which furnishes a good approximation for stable nuclei. Atomic mole is defined as the number of grams of an atomic compound that contains exactly one Avogadro number of atom. That is, Avogadro number is denoted by Na and whose value is 6.022 into 10 raised to 23 atom per mole. Atomic mass number A is of all elements is defined such that a gram of every element contain exactly Na atoms, that is Avogadro's number of atoms. For example, 1 mole of cobalt 60 is 60 gram of cobalt 60. 1 mole of radium 226 is 226 gram of radium 226. Now, molecular mole. Molecular mole is defined as the number of gram of a molecular compound that contains exactly one Avogadro's number of a molecules. Right, that is, the value of Avogadro's number is Na is equal to 6.022 into 10 raised to 23 molecular per mole, and mass of a mole is the sum of masses of all atoms that make up the molecule. For example, 1 mole of water, that is H2O, is 18 gram of water. Then next is atomic mass. Capital M is expressed in atomic mass units, that is U, 1 units is equal to 1/12 of the mass of a carbon 12 atom, or 931.5 mega electron volt per coulomb square. Atomic mass m is smaller than some of the individual masses of constituent particle because of intrinsic energy associated with binding the particles, that is nucleons, with the nucleus. Nuclear mass, that is m, is defined as the atomic mass with the mass of atomic orbital electrons subtracted, that is m is equal to m into zme, where m is the atomic mass and binding energy of our orbital electrons to the nucleus is neglected. In nuclear physics, the convention is to design the nucleus where x as azx, where a is the atomic mass number and z is the atomic number. For example, cobalt 60 nucleus with the z is equal to 27 protons and a is equal to 33 neutrons, and is identified as cobalt 2760. Now next is radium 226 nucleus, which is having 88 protons and 138 neutrons, and it is identified as radium, that is Ra 88 226. So this was, we have completed basic definitions of atomic and nuclear structure. Now look into the first and successful model of an atom, which was put forth by Rutherford. Rutherford's atomic model is based on result of the Geiger-Marsden experiment of 1909 with 5.5 mega electron volt alpha particles. They are scattered on the gold foils with the thickness of the order of 10 raised to minus 6 meter. So if you look into the two diagrams that are given below, the first one is the Thomson atomic model and the second is Rutherford atomic model. Thomson said that there are equal number of positive and negative charges in the atom, and both are roaming anywhere in the particular atom. But Rutherford said that the positive charge is bigger than the negative electrons, and the positive charge is concentrated only at the center of the atom, and negative charge are revolving around in orbit around the central positive charge. So this was the difference between the Thomson model and Rutherford's model. At the time of Geiger-Marsden experiment in 1909, Thomson atomic model was the prevailing atomic model, and it was based on assumption of positive and negative electron charges of the atom were distributed uniformly over the atom, and it was the plum pudding model of an atom. Geiger-Marsden found that more than 99% of alpha particles incident on the gold foil were scattered at the scattering angles less than 3 degree, and that the distribution of scattered alpha particles followed by Gaussian shape. Geiger and Marsden also found that roughly 1 in 10 raised to 4 alpha particles was scattered with the scattering angle exceeding 90 degree, having probability of 10 raised to minus 4. This finding was in drastic disagreement with the theoretical prediction of 1 in 10 raised to 3500 resulting from Thomson atomic model, that is the probability of 10 raised to minus 33,500. Then next is Ernest Rutherford. They concluded that the peculiar result of the Geiger-Marsden experiment did not support the Thomson atomic model, and proposed the currently accepted atomic model, in which the mass and positive charge of an atom are concentrated at the nucleus, and the size of this nucleus is in order of 10 raised to minus 15 meter. The negatively charged electrons revolve about the nucleus in the spherical cloud in periphery of the Rutherford atom with the radius of order 10 raised to minus 10 meter. Based on his model and four additional assumptions, Rutherford derived the kinematic for scattering of alpha particle on a gold nuclei using basic principle of classical mechanics. So the four assumptions are related to the mass of a gold nucleus, then scattering of alpha particles, penetration of a nucleus, and kinetic energy of alpha particles. The four assumptions are: Mass of the gold nucleus, that is capital M, is very much greater than mass of an alpha particle. Scattering of alpha particles on atomic electrons is negligible. Alpha particle does not penetrate the nucleus, that is there are no nuclear reactions occurring. Alpha particles with kinetic energies of the order of a few mega electron volt are non-relativistic, and the simple classical relationship for the kinetic energy of the alpha particle is valid. Now, next theory is put forth by Niels Bohr after Rutherford in 1913, which was combined Rutherford's concept of a nuclear atom with the Planck's idea of quantized nature of a radiation process. And he developed an atomic model that successively deals with the one electron structure, such as hydrogen atom, which is singly ionized helium, and etc. Um, M is the nucleus with the mass capital M. Me is the mass of an electron, and Rn is the radius of electron orbit. Now, Bohr's atomic model is based on four postulates. First is electron revolved about the Rutherford nucleus is in well-defined allowed orbit, planetary-like motion. Second postulate, while in orbit, the electron does not lose any energy despite being constantly accelerated. No energy loss while electron is in allowed orbit. Then third is angular momentum of the electron in an allowed orbit is quantized. So quantization of angular momentum. Then fourth postulate is an atom emits radiation only when a electron makes transition from one orbit to another, that is energy emission during orbital transition. Now look into the four postulates. First is planetary motion of electron. Electrons revolve about the Rutherford nucleus in well-defined allowed orbit. Coulomb's force of attraction between the electron and positively charged nucleus is balanced by centrifugal force. Then second postulate is no energy loss while electron is in orbit. So when electron is in orbit, it does not lose any type of energy despite being constantly accelerated. And this is a direct contravention of the basic law of nature, that is Larmor's law, which states that any time of a charged particles is accelerated or deaccelerated, part of its energy is emitted in the form of photon, that is Bremsstrahlung also tell that. Then the third postulate is all about quantization of angular momentum. Angular momentum, which is L is equal to m into r of electron in an allowed orbit, is quantized and given as um quantum number, that is h bar is equal to h upon 2 pi. So where n is the integer referred to as a principal quantum number. Then the lowest possible angular momentum of an electron in an allowed orbit is L is equal to h bar, and all atomic orbitals electron angular momenta are integer multiples of h bar. Then the fourth postulate is all about emission of photon during atomic transition. Atom emits radiation only when an electron makes transition from an initial allowed orbit with quantum number Ni to a final orbit with quantum number Nf. So the energy of emitted photon equals to the difference in energies between the two atomic orbits. That is H is equal to Ei into Ef minus E. Then radioactivity. The new topic is radioactivity, which is the process by which an unstable nucleus, that is parent, decays into two nuclear configuration, that is daughter nuclei, and that may be stable or unstable. If the daughter is unstable, it will decay further through a chain of decays until a stable configuration is attained. So the Henry Becquerel, which is also known as the father of radioactivity, he discovered the natural radioactivity in 1896, and the other names also used for radioactive decay are nuclear decay, nuclear disintegration, nuclear transformation, nuclear transmutation, and radioactive decay. So the radioactive decay involves the transition from a quantum state of a parent P to quantum state of a daughter D. Energy difference between two quantum states is called as decay energy Q. And this decay energy Q is emitted in the form of electromagnetic radiation, that is gamma rays, or in the form of kinetic energy of reaction products. Activity represents the total number of disintegrations, decays of a parent nuclei per unit time. SI unit of activity is the becquerel, that is 1 becquerel is equal to 1 s raised to minus 1, that is 1 per second. Both becquerel and hertz corresponds to per second, yet hertz express frequency of a periodic motion while becquerel express activity. The older unit of activity is the Curie, that is 1 Ci is equal to 3.7 into 10 raised to 10 per second, originally defined as the activity of 1 gram of radium 226. Currently, the activity of 1 gram of radium 226 is 0.988 Ci. Decay of a radioactive parent P into stable daughter D. Rate of depletion of the number of radioactive parent nuclei is equal to the activity at a time t, and it is also represented by the formula which is given here, where n is the initial number of parent nuclei at a time t is equal to 0. Number of radioactive parent nuclei as a function of a time is also given by the following formula. Then activity of a radioactive parent is as a function of a time is also given by the following formula which is given below, whereas A is the initial activity at time t is equal to 0. Now this is giving you the parent activity which is plotted against the time t, and the graph shows that exponential decay of the activity and concept of half-life and the concept of mean life. Now look into the half-life, which is symbolized as T half of a radioactive parent P is the time during which is the number of radioactive parent nuclei decays from the initial value, that is n is equal to 0 at time t is equal to 0 to half the initial of its value, and this decay constant and half-life are related as the lambda is equal to h upon t half. Now have a next point, that is radioactivation of a nucleids, and this is occur when a parent nucleid P is bombarded with the thermal neutrons in a nuclear reactor and transformed into radioactive daughter nucleid D that decays into granddaughter nucleid G. Now the probability for radioactivation to occur is governed by the cross section for the nuclear reaction and neutron fluence rate, and unit is barn per atom, where whereas 1 barn is equal to 1 B, or it is equal to 10 raised to 24 centimeter square. An important example of nuclear activation is the production of cobalt 60 radionuclide through bombarding a stable cobalt 59 with the thermal neutrons. Here for cobalt 59, the cross section is 37 bar per atom, and typical reactor effluence rate are the order of 10 raised to 14 centimeter square per second. Radioactive decay is a process by which unstable nuclei reach more stable configuration, and there are four main modes of radioactive decay. First is alpha decay, second is beta decay, third is gamma decay, and fourth is spontaneous fission. Nuclear transformation is usually accompanied by emission of energetic particle, that is charged particle, neutral particle, photons and neutrons. So radioactive decay and the particles which are emitted are in alpha decay the particles emitted, beta plus decay the particle or positron or neutron are emitted, beta minus decay or electrons are emitted, electron captured, electrons are emitted, pure gamma decay anti-neutrino are emitted, then internal conversion photons emitted, and in spontaneous fission orbital electron fission products. In each nuclear transformation, a number of physical quantities must be conserved. So, most important physical quantities are total energy, momentum, charge, atomic number, and atomic mass number, that is, mass number of nucleons. So, these all physical quantities must be conserved in nuclear transformation. Now, Henry Becquerel discovered alpha decay in 1896. George Gamow explained its exact nature in 1928 using quantum mechanical effect of tunneling. Heinz Geiger and Ernest Marsden used 5.5 mega electron volt alpha particles emitted by radon 222 in their experiment of alpha particles scattering on a gold foil. Kinetic energy of alpha particles released by naturally occurring radionuclides between 4 mega electron volt and 9 mega electron volt. And gamma decay is a nuclear transformation in which an excited parent nucleus P, generally produced through alpha decay, beta minus decay, or beta plus decay, which attains its ground state through emission of one or several gamma photons. Atomic number Z and atomic mass number A do not change gamma decay. In most and alpha and beta decays, the daughter de-excitation occurs instantaneously, so that we refer to emitted gamma rays as if they were produced by the parent nucleus. If the daughter nucleus de-excites with the time delay, the excited state of a daughter is referred to as a metastable state, and the process of de-excitation is also called as isomeric transition. So here we have successfully completed the introductory part as well as atomic and nuclear structure, and the conclusion or the summary of basics of radiation physics, and some more topics are remain from this chapter, so that we will look into the next video. Till then, thank you and bye bye.